All right. Okay, so let's go back to the problem of how to compute the principal components, right? All we need to know is to really how to first define the problem and then solve it computationally. So because we want to find such a unit length vector, which is u, and we don't know it, so it's just write it. We just write it as u1 and u2 as a vector. So and assume that the length. Assume that's the length of our projection, right? Because it's two-dimensional, so we can use the these two element vector x tilde I, which is the original data, right? We want to know the length of projections of these original data, which is of course first normalized, right? We have tilde to each dimension. So that is the data points. We want to compute the projection of this vector onto the unit length vector u. So the projection is actually can be computed. The length of the projection can be computed by the inner product between the two vectors, right? We have two vectors, right? They shape they are like within the angles between them is something we know, right? So we can basically compute the dot product between these two vectors in order to compute the length of projection. I think we have this something similar covered in the SVN when we use the projection to measure the distance between a point to a vector, right? So anyway, we have this inner product that is the projection length for that data point. Okay, and then we just need to sum up all those projections, right? So, and of course, there's one more step, which is to compute the square, right? It's the sum of squares. It's not the projection itself, because the projection can be negative or positive, right? But we're interested to see the magnitude of the projection. So ultimately, we just need to compute the square of it, and then sum up all the squares. Give me a second. Let me enable the virtual background. All right, looks better. All right. So that is how we define the sum of squares. So, right, we have this very long equation, and that is our goal to maximize, right? Remember, we want to maximize the sum of squares so that we have larger variance along that dimension. Okay, so it's we're getting into a kind of a optimization problem, right? We kind of define some function, objective function, which is the sum of squares, which looks like this way, right? So let's try to make this whole equation simpler, right, into a simpler form. So because our data, if we put it into a matrix, it looks like this. It's two-dimensional, and we have assume that we have m data points, so that will be a 2 by m matrices, all normalized. So this capital X also comes with a tilde symbol. Okay, so that is our data, right? And actually, the sum of squares, if we put it into the matrix multiplication form, it actually can be written in this way, into the matrix multiplication form, right? The x x tilde is 2 by m, right? And it's really hard to write on this laptop. And the x is 2 by m, and x tilde is m by 2. And so the two matrices multiplied together will be a 2 by 2 matrices, right? And the the U to though U transpose will be 1 by 2, and the U will be 2 by 1. So all these matrices multiplied together will be just a scalar number, which is just a single number, and which is has the same mathematical meaning with this summation equation. Okay, so that's something you can work on it on your paper if you write down all those matrices and try to map all those matrix multiplications with the first column with the first row, right? Second column with the second row, and so on. So that is the matrix form as the sum of squares. So now we can simply rewrite the question into as this form. We want to maximize this sum of squares, right? And in order to make it easier for the next stage, we can put a 1 over n here, which is kind of a normalization term, right? But which didn't really change the nature of this sum of squares. So essentially, we want to maximize this term, right? But it comes with some constraints, right? We must have this constraint that this one has a unit length equals 1, right? Otherwise, there could be multiple. Otherwise, the problem is unbounded, so the optimization will never converge. Okay, so it looks like we have a very typical optimization problem. We have some goal to optimize, and we have also need to comply to some constraints, which is to make sure that the target vector is of unit length, right? Which has a norm. A 1 as its Euclidean norm. Okay. All right. So let's put this into this square, and now let's just think about how to solve this problem. Right. This must remind you of some similar problems that we have came across this semester. For example, in SVM, it's also it's also the optimization problem. But here we have a simpler form of optimization. So first of all, the constraints is a equation. It's not an inequality, right? Remember, in SVM, we have an inequality as the constraints. So we need to have we need to make it a duality problem. But here we don't have inequality, but we just equation. So if just the equation, the norm of U equals 1 makes it really much easier to be solved with a Lagrangian multiplier method. Okay, so if we rewrite it into this form, the whole matrix multiplication looks like this, right? And if we look at the nature of each, so first of all, it's x tilde and x tilde times x tilde transpose that we are looking at here, right? So within here it's x tilde, and here it's x tilde transposed. So the first column here is equivalent to the first row here, right? And by the rule of matrix multiplication, we need to compute the dot product between these two parts, right? The dot product between these two parts, which results in this quantity, right? Which is just the summation of this variance of x1, right? So that is the meanings of these different terms. Okay, and basically those variance and covariance, they measures how much the two features vary, and how much the covariance measures how much the x1 and x2 are related. Okay, all right, so that is the meanings of these matrices. So in order to solve this maximization problem, we basically need to use a Lagrangian multiplier. Okay, remember, we just need to introduce a new variable, which is lambda, which is our multiplier. Okay, so this lambda becomes is the new variable that we introduce, and we just use the original form of the objective function, which is here, subtract this lambda times these constraints. The constraints is an equation, so we can move one towards to the left of the equation and use lambda times that equation, which makes the Lagrangian term. Okay, so we construct this Lagrangian term, which is in this form, and now we convert the problem into maximize this Lagrangian with respect to both u and lambda. Okay, we have additional variables here. Okay, so now we can take a usual step, which is to take the derivatives of this Lagrangian with respect to the variable, which is the vector u, right? So taking the derivatives of a vector, which is similar to taking the derivatives of a scalar number. So you can view this first term as if it is a quadratic term. So taking a derivative of it will remove the transpose term, and taking a derivative with respect to this will remove also one u. Okay, so this will result in this formula, right, which is 0. Okay, so that is the results of taking derivatives and make it 0 so that we can compute the extreme values. And if we simplify it, if we move the lambda times u to the right, then we have something like this. So this equation actually it's the definition of the term of eigenvector in linear algebra. Okay, so the definition of the eigenvectors for this matrix within this chunk. So this is a matrix, right? The matrix, let's call it A. If A times a vector u equals lambda times u, right? Then we say the u is the eigenvector for the matrix A here. Okay, so we just need to solve the eigenvectors for this composed matrix. Okay, so let's have a little bit review of what eigenvector is. Okay, so basically we have converted the goal of maximizing the sum of squares into the problem of finding the eigenvectors of the covariance matrix. Okay, so yeah, here eigenvector it's first invented by in Dutch, and it basically means my vectors, and what it means is that a matrix, a square matrix, and a column, given a square matrix and a column vector, if we times that matrix with a vector, it will not change the direction of that vector. Okay, it will only applies, it's only equivalent to applying some factor, like applying some number lambda to it. Okay, and if this equation satisfies, then we say V is the eigenvector of A and the lambda is the eigenvalue. Okay, so the eigenvector always comes with the eigenvalue, which is the factor here, the lambda factor here. Right, so which means this linear transformation defined by the matrix will not change the direction of the vector. Okay, which will only change the magnitude of the vector. Okay. All right. So let's further take some reviews. Okay. So these reviews will be some of the bases for our next step computation. Okay. So the first is called a spectral theorem. Okay. So basically, it says that it determines the number of eigenvalues and eigenvectors. If we have a square matrix, which is n rows and n columns, and it's also symmetric, which means if we transpose that, if we transpose the matrix A, it will be itself. Okay, so it's symmetric along the diagonal line. So then we say it's orthogonally diagonalizable and has only real eigenvectors. Okay, so in other words, if A is n by n and symmetric, then we must have n eigenvalues from lambda 1 to lambda n, and n non-zero real eigenvalues, eigenvectors. Okay, which means we will have n equations that satisfy this way, which is A times Vi equals lambda I times Vi. Okay, so that is a theorem from linear algebra. So based on this theorem, so if we have some non-symmetric matrix, for example, if we have a m rows and an n column matrix, right, which is not a square, which is not symmetric, but we can construct some symmetric matrices by use A times A transpose or A transpose times A. Then the resulting two matrices, they are both symmetric. Okay, so that's something we can know about. Okay, and by the spectral theorem, because we have A times A transpose and A transpose times A, they are all symmetric, then they share the same non-zero eigenvalues. Okay, so for example, if say V is the non-zero eigenvector for A transpose times A, right, with some eigenvalue, which means we have this equation like this, right? That is by the definition of eigenvalues and eigenvectors. Then if we multiply both sides with A, then we can have the following equations, right? Which means we can associate the A with A transpose times some vector here, and then equals lambda times the same vector, right? So which means that the lambda is also the eigenvalues for A, the eigenvalues for A transpose times A is also the eigenvalues for A times A transpose. Okay, so this is a very useful property for our usage, because the shape of A transpose, A times A transpose, and A transpose times A will be very different depending on what is your M and N, right? So if you have a lot of data, then your M can be very big. Otherwise, if you have very large features, if you have a lot of features, then your N will be very big. Okay, so that depends on, so depending on which quantity is larger, then you can decide which matrix you use. Okay, so the usage is like, say, if you have a lot of the number M is much larger than the N. Say if you have no, it's the other way. So if your N is much larger than M, then you have an A, which is a very thin matrix, 2 by 500, for example. Then the quick way to find the eigenvalues for a 500 by 500 matrix, right, resulted from this A transpose times A, right? Because A transpose is 500 by 2, it times with A, which results in a 500 by 500 matrix. So we can basically first, rather than compute this directly, we can compute A times A transpose, which is just a 2 by 2 matrix. Then to such a small matrix, it's much easier to find its eigenvalues and eigenvectors. Okay, and all these eigenvectors are shared. And based on the spectrum theorem, all the other 498 eigenvalues for AT and A transpose times A are all zeros. Okay, so that is a interesting and useful theorem we can use in computing the eigenvalues and eigenvectors. Okay, so let's further look at this the computation. Okay, say when we have a data set in X in such a dimension, it's 2 rows by m columns, and if we compute x tilde times x tilde transpose, then this matrix will be 2 by 2 matrices. Okay, will be a 2 by 2 matrix, right? Because it's 2 times 2 matrix times a m by 2 matrix, which will eliminate the dimensions in the middle, which results in a 2 by 2 matrix, which means there are 2 eigenvectors and the eigenvalues, right? We have, so we will use this sigma symbol to denote this matrix multiplication, denotes this covariance matrix. So it doesn't mean summation, okay? In this case, the sigma doesn't mean a summation here, okay? And so assume that we have a larger eigenvalue, which is lambda 1, and the lambda 2 is a smaller eigenvalue. Then the total variance in data is simply the summation of lambda 1 plus lambda 2. So the PC1 U1 will account for lambda 1 over this total summation of the total variance, right? And PC2 is the remaining, PC2 accounts for the remaining part of variance, okay? So what if our X data set has higher dimensions, have larger than 2 dimensions, okay? We can basically do the same thing, right? So the results of this matrix, of this covariance matrix, it will be an n by n matrix, right? Which means there are n eigenvectors and n eigenvalues, right? We will have n equations like this, okay? And we can basically sort all the eigenvalues in such a way, and then the total variance will be the summation of all the eigenvalues, and the PC1 accounts for that many of the total variance, and so on. Okay, so that is basically how we do the PCA with data from scratch. Okay, so the key step is to find the eigenvalues and eigenvectors, right? Once you first compose the covariance matrix, and then you use some method, some linear algebra method, to find the eigenvalues and eigenvectors for that covariance matrix, then the resulting eigenvalues are just the principal components for you to choose from. You can choose whatever numbers you want. You can choose the first 2 principal components. So that'll be the 2 dimensions. You can reduce the original data or the original data set too. So the resulting data will only have 2 dimensions, which means you can plot those data along these 2 dimensions. Okay, so let's look at the next slide for how to find the eigenvalues and eigenvectors in Python using NumPy. Okay, so it's actually a very straightforward line of codes to use. Like, given a data set, you just use the linear algebra components of NumPy, and the eigen function when you applied it to the dot product, when you applied it to the covariance matrix, which will return you the eigenvectors, the eigenvalues, right? The first one is eigenvalue and the second one is eigenvector. So you can see that the first eigenvalue is much larger than the second one, which means that the PC1 explains the vast majority of the total variance among the data, right? It's 386 as opposed to 7. And the second, the PC2 only explains a very little proportion of variance. Okay, so I think that is the typical patterns in a lot of data sets. Okay, even if you so if you have more than 2 eigenvalues, eigenvectors, or you have more than two PCs, you have like 3, 4, or 5. Then if you look at the distribution of those eigenvalues, you will find that the PC1 will take the vast majority of it. And the only, usually speaking, you can just use PC1 and PC2 or PC plus PC3 to represent the vast majority of the total variance in the data. Okay, you don't necessarily it's not necessary that you use all the PCs to represent the data. All right, now let's take a look at the next one. So after we have got all the PCs, what is the next step? Okay, so we actually have a lot of freedom to do a lot of interesting operations, right? We can like choose to reduce the data to k dimensions, right? We have say our original dimension of data is n, right? We have an n by m because so it's n rows, and that is n features. And the covariance matrix is also n by n matrix, and which means it will have n eigenvectors, right? So we can selectively choose k dimensions, right? We can choose to keep k eigenvectors from u1 to uk, and with the top k eigenvalues, right? Of course, we want to keep those eigenvectors that have larger eigenvalues, right? Because they account for larger variance in the data, right? Say we have these k eigenvectors selected, we can stack it into a matrix, which makes a n by k matrix. That is our matrix U, okay? And then we can use that matrix to basically create a k-dimensional subspace, okay? That is also the meaning of this matrix U. That is the basis for a k-dimensional subspace. Okay, and we can use that U to project our data points into this subspace, right? We can, for example, given any data points, xi, which is n dimensional, right? We can use U transpose times xi to project this n dimension data into this k dimensional data. Okay, so this projected k dimensional data will just be the lower dimensional representation of the original one, right? And we can project m example into the new subspace at the same time, right? We can just directly use select the original, use the original data times the U transpose, right? Which will give us a new projected data points, right? Which is in k dimensional space. Okay. So in this way, we can successfully reduce the n-dimensional data into k-dimensional space. All right. So for visualization purpose, this k can be very small, right? We can only visualize 2-dimensional or 3-dimensional space, dimensional data. Okay. All right. So let's look at the next, which is the covariance matrix of the transformed data. Okay, so if the y is the transformed data or the project data resulted from the previous step, okay, a significant characteristic of it is that if we look at its covariance matrix, which is the defined by y times y transpose, right? But since y is the results of U transpose times x, so we can substitute the computation of y into this equation, which gives us this equation, which means we put x into the middle, right? So that is the covariance of the projected data, and we know that it will be a diagonal vector because U is the eigenvalues, U is the eigen vectors. So the results of this will be a diagonal matrix that's only there is non-zero values along this diagonal line, and all the others are zeros. Okay, so that is an interesting property of the covariance matrix of the transformed data. Okay, so all variance between all those values in different dimensions, they are all zero, which means the features are independent. Okay, so the i's feature is not related to the j's feature at all in this projected new space. So that is a second advance that we can get from the PCA analysis. Okay. So the covariance matrix actually is related to shape of data. Here, if we look at the general patterns here, say this feature, if a data look like this, it looks like very narrow, right? And the covariance matrix usually looks like this. The covariance terms are very small. Okay, the ones here means that the x-axis and the y-axis, they are not related to each other a lot. And in the second example, if the two matrices if the data looks like this, that means the two features, they are kind of correlated, which means they have larger covariance in this non-diagonal values. Okay. All right. So we have just introduced in a Python page, we have the code available for directly call the eigen function, right, to compute the eigenvalues. But in practice, we have another, more efficient way to conduct PCA, which is a faster way. So it's called singular value decomposition. Okay, or SVD for short. Okay, so it doesn't need to use this method. You don't need to compute the covariance matrix as we did. We actually can directly decompose the data itself. So if the data is n by n column, n by n dimensions, then we can call SVD, which will result in three matrices timed together. The first one is an n by n unitary matrix, and the second one in the middle is the n by n rectangle diagonal matrix, and the third one is an n by n. Okay, so the meaning of it is that the sigma in the middle is the square roots of the eigen oh, actually not really. If we the vector here, the first vector, the n by n unitary vector here, is just the principal directions. The principal component directions. And the sigma, if we use sigma square, it will be the eigenvalues. Okay, it will be a square of singular values. So it's kind of a more computationally speaking, it's faster than directly compute the eigenvectors and eigenvalues for these matrix, and it's also more commonly used because of its numerical stability. Okay. All right. Let's summarize a bit and look at a concrete example of PCA. So basically, we just need to normalize the data, right, from x to x tilde, and then we've just composed the covariance matrix, and then find the eigenvectors and eigenvalues for that covariance matrix, and then we can select a small number of eigenvalues with the corresponding eigenvectors, so that we can project the original data into a subspace with lower dimensions. Okay, and we can use these principal components selected to explain the original data, like to explain which are the most important features, for example. Okay, so The first application, let's look at this slide. It's for better interpretation of features. Say, let's go back to the bird database, right? We have length, wingspan, and weight, right? If we compute the weight the covariance matrix looks like this. And if we find the eigenvalues, it will be like this, and eigenvector looks like this. Okay, so those features mean that the PC1 is 22% times length plus 41% times wingspan plus 88% times weight. So it kind of basically characterizes the size, right? Because all the coefficients are positive numbers. But if you look at PC2, right? If you look at PC2, it'll be like 25% of length plus 85% of wings minus the weights. So the weight is a negative factor here. So it's kind of characterize the stoutness feature of the bird, right? So we can use those PCs, principal components, to kind of get more informative interpretations out of the data. So a second application is data compression. Okay, because we basically applied project the data from a higher dimension to a lower dimensional space, which basically means we reduced a lot of dimensions, and then we saved storage space. Like we removed some non-informative and unrelevant features. Only select those, only keep those that are relevant in terms of variance, how much variance it can explain in the original data sets. Okay, so the last example I want to show is the example called Eigenface. So it's a method for using PCA for face recognition. So it's a famous example, actually. For example, the face image we have in can be very large, right? And 100 by 100 pixels is nowadays is small. It's just a small data set, a small, very small, tiny image, right? But I just use this number for example here. So our images, face images, like is 100 by 100, which means if we flatten each image to a column vector and stack them, it will be it's 10,000 by m matrices. That'll be our whole training data sets, right? So whole data sets. So what we can do is to compute the eigenvalues and eigenvectors of the covariance matrix, which is 10,000 by 10,000. Okay, and each eigenvector is also a 10,000 dimensional vector. Okay, so if we get the eigenvector and then reshape it back to 100 by 100, then it can be seen as a face image. That's the so-called eigenface, and that eigenface will be used as the basis for face comparisons, because given any new face, we can project that new face onto the eigenvectors selected, onto the eigenfaces selected, and the projected face can be the basis to to tell whether the new face is from a new person or from a outside member, for example. So it's very useful to in image recognition, in face recognition tasks. Okay, so for example, if we these are eigenfaces, 10,000 eigenfaces can be used to represent new faces, and in theory we don't need to use all those 10,000 eigenfaces, right? We can only use a small subset of it and use a new image to project a new image vector to a selected subset of eigenfaces, not all the 10,000 eigenfaces. And the projection can be used as kind of the identity for the new face. Okay, so in practice, we only choose 100 to 150 eigenfaces which is usually very sufficient in usage. Okay, so this is how an eigenface looks like. So that's the first eigenvector. That is the first principal component. So it's not like a recognizable human face, but it's really characterize the most amount of variance in all the face data. So in the assignments that I'm going to release this week, we will play around with a eigen, not eigenface, but eigenhand example, because we in our previous assignments we look at the hands data structure, the hands digit data, right? So we will look at if we can use the same technique for hands recognition. Right. So I think that's so much for it today.
Do you mind if I ask a question about assignment 8?
Yes.
Okay. So one of the things that I had is in task 1, when it gives you the data 0, I was getting very different numbers than your projected ones. And I'm curious if that is supposed to be random each time, or if we're supposed to get the exact values that you have.
Excuse me. Give me a second. Can you say that again? Sorry.
Yeah. So in task 1 of assignment 9, I'm sorry. What I am getting for data 0 in the first task is very different than what you get for data 0. And then for the rest of the tasks, I'm able to get all of the results as expected, but my data 0 does not match yours at all.
Okay. I think I had the same issue in my test several times. So I guess it's the problem of PyTorch.
Okay, yeah, because when I run it over and over again, it's new each time.
Yeah, okay.
So yeah.
I see. Yeah, it's just the way of the random seeds, I guess.
Okay.
Yeah. Cool. It's not an issue. Yeah. Thanks for having this. Yeah. Okay. So I see the question. There are 9 assignments. Yeah. So actually, so what I can do to that, because I made a little change. There's some new contents in this semester as to my previous semesters. For example, the word embeddings is the new assignment that I add to this semester. So there's one more question than expected in the syllabus. So that is I would say a change to the number of assignments in syllabus. So what I can do for you, if you mind, I can like select 9 best assignments for you in those 10 assignments submitted. But I would say if you all submitted your assignments and get the expected answers, I don't think it will be a significant influence to the total scores. Yeah. So if you have concerns or questions, you can let me know. We can chat offline. Okay. Thank you. All right. Thank you, guys. We'll see you again on Thursday. Bye-bye.